Good afternoon, ladies and gentlemen. Welcome to Physics 30 Atomic Physics Lesson 10, Mass Defect and the Binding Energies Revisited. Now, I'm going to talk about mass defect again, just because I can. So in theory, when a nuclear reaction takes place, some energy is lost to the surroundings or to a particle produced. This energy originates from a change in mass and can be found using the relationship change in mass is the mass of the parent minus the mass of the products, or in this case, parent minus daughter. Nuclei, but we talk about products because, of course, there's stuff besides nuclei made. Anyway, now mass is seldom given in kilograms as this unit is clumsy for small particles. Instead, the atomic mass unit, U, is used. And note once again, this is, for these calculations, you have to use the more advanced, the more accurate one than the 1.66 times 10 minus 27 on your formula sheet. Anyway. Masses of most radioactive isotopes were given on the mass defect handout and are listed on page 881 of the textbook. So that handout from section 5, if you can't find it, it's page 881 of the textbook. And note, remember the alpha particle, alpha, and that's the alpha symbol, is the helium-4 nucleus and has a mass of 4.002603 atomic mass units. And the second thing to note, the mass of a beta particle, beta negative, electron, or beta positive, the positron, is not given on this chart, but it is 0.000549 units. Okay, really quite small. Now, and recall, mass defects are converted to energies using E equals mc squared. If you use the more accurate value of C equals 2.997925 times 10 to the 8 meters per second for this calculation, you will get the following more accurate conversion factors. Now, somewhere in the textbook they do these. I'm not going to bother. If you want to go do the conversions yourself, you can. But one atomic mass unit is 1.49 times 10 to the minus 10 of a joule, E equals mc squared. And one atomic mass unit is 931.4941 mega electron volts. So remember these for your calculations. They're not in your formula sheet. Write them down somewhere. Okay? Yes, I will give them to you on a test if you have to do the calculations. All right. Now, mass defect and binding energy between nucleons in the atom. The first examples ask you to find the binding energy in a single atom that is not undergoing any sort of nuclear decay. For these problems, the masses of protons and neutrons are needed. And once again, here are the mass of protons and neutrons, more accurate, or more precise, I should say, than what's on the formula sheet. Now you got me thinking, accurate or precision? Precise, I think. Anyway, so the differences in the binding energy of the electrons are small enough to ignore most nuclear calculations. Thus, for this type of calculation, no electron mass is used. We don't count the electrons, because sometimes we're dealing with ions, and frankly, the mass of the electrons added together are so small we don't care. So, warm-up problem for you guys. The actual mass of copper-63 is 62.9298 atomic mass units. What's the mass defect? Okay, well, let's start off. 6329 copper. That's atomic number, number of protons. The atomic mass is the top number, number of neutrons and protons. So, 63 minus 29 is 34 neutrons. So we go 29 protons, 29 times 1.007825 is 29.226925 atomic mass units. 34 neutrons, 34 times 8665 units is, too fast, 34.294610 atomic mass units. So, in theory, the mass is 63.521535 units. Actually, 62.9298. 62.9298. Now, is that it? Actually, go back to your handout for chapter 5. Oh, sorry. My apologies, ladies. Got the feeling there's more decimals to that, and I might have forgot to write it out. So we go back to our handout for section 5. And copper. I don't have it. Oh well, we'll just use this number for the moment. Mental note, go back and fix it. So missing mass is 0.5917 atomic mass units. And notice right about where the 7 is where we start counting the electrons. So yeah, we can round it off there. Because we don't know the number of electrons, so yeah, that's as good as we can get for this. All right, so that's the missing mass, or the mass defect. Okay, now notice this is a part A. Oh, come on. Part B, what is the binding energy per nucleon? Okay, 0.5917 units. Well, traditionally, its binding energy is megaelectron volts, so we just said it was 931.4941 megaelectron volts per 1 atomic mass unit. So that's 551.165059 megaelectron volts. No, that's too many significant digits. You're right. Anyway. Binding energy, nucleon, 551.1, round off 17 electron volts. No, don't do the rounding off in your calculation to the very end. And double checking, this is copper 63, so that's 63 nucleons. 8.748 mega electron volts per nucleon, which makes it quite stable. Not the most, actually really quite close to being the most stable. So you won't get this to work well in a nuclear fission or fusion reaction. Okay, so far so good? I hope so. Now, mass defect and binding energy during alpha decay. So, during alpha decay, a parent isotope decays into a daughter particle, or daughter isotope, and an alpha particle. If we assume the parent starts at rest, and most atoms are at rest when making up a block of sample undergoing decay, the binding energy released is transferred to the energy in the alpha particle by conservation of energy. Okay, so what happens here? We have our parent. It undergoes decay. Now notice this is the atom bound to other atoms. Then it becomes what? The daughter, still bound. And we have an alpha particle. What do we know about alpha particles? The gas. So that energy, that mass defect becomes energy, kinetic of the alpha particle flying off. Okay, so what's the maximum kinetic energy in mega electron volts of an alpha particle in the alpha decay of U-238? Okay, U-238. Now, 238 is the mass number. The atomic number, the number of protons for uranium is 92. So to undergo alpha decay, so I write out the alpha particle, and I write it last because usually we're more interested in the daughter particle. Now, what is the daughter particle? I don't know. But 238 minus 4 is 234. 92 minus 2 is 90. So what is an atomic number of 90? I believe it's thorium. Do I really care? No. but I do expect you to be able to come up with an alpha decay. And yeah, there's probably a neutrino or a gamma particle or some weird freaking thing out here. Who cares? We ignore that. It doesn't exist. Well, it does, but the amount of energy and mass it absorbs is relatively small. Okay? So, where was I? Yes. U238, go to our chart, is 238.050788 atomic mass units. Thorium, 234, according to our chart, is 234.043601 atomic mass units. And our alpha particle, excuse me, is 4.002603 units. So, mass defect. Remember, we're subtracting these. We get, not much, 0.004584 atomic mass units. Okay? Now, converting that to mega electron volts, 0.004584 units, 931.4941 mega electron volts per 1 unit gives me 270 mega electron volts. So that's the energy kinetic of the alpha particle. Now that leads, sorry, I'll stop for a moment, just make certain you got that. Standard mass defect, turn that mass defect into energy. We use the shortcut rather than doing E equals mc squared. And that, of course, leads to the crux of this lesson. What's the maximum velocity of the alpha particle after it's ejected? Well, we have 4.270 mega electron volts. All right. Now, that's what we calculated. Now it is 1.60 times 10 to the minus 19 of a joule per 1. Oh, sorry, that's electron volt. I have to convert this. My apologies. That's 4.270 times 10 to the 6 electron volts. So 4.270 times 10 to the 6 electron volts. 1.60 times 10 19 of a joule, 1 electron volt, 6.832 times 10 to the minus 13 of a joule. Now, yes, there are other ways to convert it. We could have gone back to our mass and converted that directly to joules, whatever. I already had mega electron volts here. Now, E sub k, 1/2 mv squared. And remember, we have to do this calculation with joules. We can't do it with mega electron volts. That's why we're converting to joules. So 6.832 times 10 to the minus 13 of a joule is 1/2. And the mass of an alpha particle, you look at the last page of your formula sheet, 6.65 times 10 to the minus 27 of a kilogram times v squared. So v squared is, actually no, I just plugged the numbers in. I got v, 1433401 meters per second. Now, that's far too many significant digits. It's about 1.43 times 10 to the 7 meters per second. Okay. Now, it's actually not quite that much due to relativity and time dilation, but that's the number we're calculating, and save this for relativistic physics in university, because we don't teach that anymore in high school, which sucks. Anyway, so this is the crux of the lesson. What's the velocity of the particle being spit out? Okay. So now, just to remind you about beta decay, during beta negative decay, a neutron is converted into a proton, an electron, a beta negative particle, and an antineutrino. Beta positive decay is the decay of a proton into a neutron, positron, beta positive or positive electron, and a neutrino. The mass defect calculations are similar to those for alpha decay. Note the mass of beta particles or neutrinos or antineutrinos are not included in these calculations. They're small enough we can ignore. Right? They're not included, so skip it. So, let me give you a typical example. How much energy is released when sodium-22 decays to neon-22? So, sodium-22, Na, that is atomic number of 11, going to neon, 22, 10, Ne. Now, part of the question is balance the equation. What do we got here? Well, we've gone from 11 protons to 10, so we're having a beta positive decay and a neutrino is emitted. And as I said before, we ignore these. Okay, so how much energy is released? And then the next obvious question, what's the velocity of the neon gas? So, excuse me. So, let's do this. Na22 is 21.994436 units. Right from that page I gave you, the notes I gave you for in Atomic 5. If not, look at page 881 of your textbook or Google it. Oh, if you do end up Googling these numbers, note they might, the last digit or two might change depending on who's done the most recent calculations. Because sometimes, yeah, particularly for the more radioactive ones, they have a very short lifespan. It can be a little bit difficult to measure, but that's life. 21.991385 units. So the mass defect. Zero 0.003051 units. All right. Now, excuse me. All right. So here we go. Now, calculating the energy, 0.003051 units times, now, going directly to joules, 1.49 times 10 to the minus 10 of a joule is 1 atomic mass unit. Doing it this way, so that I don't, excuse me, so that I don't have to bother going to mega electron volts and then electron volts and all that. Now, 3051. And of course, I'm doing it a different way, so I haven't done the calculations yet, but help me as we go along. 49. This is 4.54599 times 10 to the minus 13 of a joule. So that is per atom. So what's the energy kinetic for that? Well, E sub k is 1/2 mv squared. So 4.54599 times 10 to the minus 13 of a joule equals 1/2. And the mass is in atomic mass units. Poopy. I forgot to... Getting old. Anyway. So, what is... excuse me. I apologize. So, 21. So that's times, let me see, 1.66. Not 1.66. Number 0.539 times 10 to the minus 27 of a kilogram is 1 unit. Excuse me. So 21.991385 times 1.660539 exponent to the negative 27 is 3.5 3.6, 3.651755 times 10 to the minus 26 kilogram times v squared. Now, running out of space, times 0.5 is and this. So I'm getting a velocity of 4989745 meters a second. 4.99 times 10 to the 6 meters a second, or 4.99 times 10 to the 3 kilograms a second. So that would be a typical question. What's the mass defect? What's the velocity? Now, I should have given you a second page to do that, but whatever. Guys, see how that goes? All right, good. Now, mass defect and binding energy during nuclear fission. In fission, an unstable nucleus breaks apart, releasing a large amount of energy. Again, finding the difference in mass between the products and reactants, and the reaction will give us a mass defect. Okay, so here we go. Calculate the energy released in the reaction. Uranium-235 plus neutron makes zirconium-97 plus tellurium-139 plus some neutrons. Now, notice I'm not saying the velocity of any of these because I don't care at this point. Well, actually, no, I do care, but zirconium and tellurium tend to be solids. I'd only ask for the velocity if we're making a gas or I'm specific about it. Anyway, now, first things first, we have to balance the reactions. Notice on the right, unknown number of neutrons. So, grab Mr. Formula sheet and look at, excuse me, I apologize, ladies and gentlemen, bit of a cold. And look at, well, the periodic table, I should say. Uranium-235. U-235 is 23592 uranium plus capital U, 10N. Zirconium-97, 97ZR. Zirconium. Where's zirconium? Zirconium. 97. There it is, 40. Atomic mass of atomic number 40. Tellurium. Te. Tellurium. 139. Where's tellurium? I'm missing. Oh, blind. Oh, mother poopy. I am blind. I apologize, ladies and gentlemen. Need glasses. Anyway, now the question is, how many neutrons do we have? Now, someone will point out we don't actually have to do all these steps because 235 and 1, 97, 139 plus something. But do it because we could have some, like an alpha particle being given off or a proton being spit out or something. So I want you to be able to do the balanced reaction right off the bat. So 235 and 1 is 236. 97, that is a difference of 3. Okay. Double check my math because I'm getting old, but I think I'm right. 36. Oh, shoot. I apologize. It's not right. I hate this. Zirconium 94. My apologies. I hate this getting old. And the last question. No, I'm not erasing this. Way too much work to redo all this just because I made one dumb math boo-boo that I didn't catch right away. Actually, it's a typo. Now, where was I? Zirconium 94. 40. That makes more sense. So So yeah, I got to double check this. Let's do my math again. Now everybody grab your calculator because Mr. Sutton's getting old and he's punishing you. 235 plus 1 is 236 neutrinos. Nucleons, sorry, over here. And how many nucleons do we have over here? 94 plus 139 is 233. Oh, he's right, it is 3 nucleons. I hate this getting old. I apologize, ladies and gentlemen. Anyway, so let's see if I can screw this up again. So, now, how can we simplify this? Let's get rid of one of these. Like a chemical reaction, we can cancel out. So uranium-235. Think about it. If we have a reactant and a product, we're not changing the overall equation. 235.043.930. That's what it says on the formula sheet. Zirconium 94, not 97, is 93.906315. Tellurium 139 is 138.934700, and 2 neutrons. 2.017330. And guys, check my math. This is getting embarrassing. I got a mass defect of 0.185585 atomic mass units. Now, I'm going to leave it to you to calculate the energy defect in megaelectron volts is 172.9. Because at this point, it's obvious they should take the calculator from me and I should go take a nap. Anyway, now, that is it for me for this section and this course. This is the last bit we're talking about. So congratulations. You've made it through all the notes. Woohoo! Anyway, go through this, see if I made any other dumb math boo-boos. And if not, work on the homework. If you've got questions, shoot me an email. Otherwise, congratulations.